Good morning, everyone. Myself, Priyadharshini, working as assistant professor in the Degree Department of R&D Engineering College. Today, we are going to see a topic from the subject digital signal processing. The topic is about FIR and IIR filters. So, under this topic, first we are going to see the realization of FIR filter. The basic difference equation for that filter is y of n is equal to the summation between k tends to 0 to m x of n minus kb of k. And we have to take the z transform. So h of z is equal to the summation k to 0 to n minus 1 h of n z to the power of minus 1. So the filters can be realized in the three different structures. One is direct form realization, cascaded form, and the linear phase realization. So the direct form realization. So considering the difference equation which is governing the FIR system. So y of n is equal to b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus b of n minus 1 plus x of n minus 1. So taking the z transform on both the sides, y of z is equal to b naught z x of z and b1 z inverse of x of z and b2. So like this, it will move up to n minus 1. The same structure can be realized by using the different components of the designing, that is delay unit or the multiplier or the adder. So x of z is my input and y of z is my output, and in between I am having the different stages of including the delay units and as well as the multipliers. And the next is going to be the cascaded form. The cascaded form is nothing but a series form, and it will be divided into the different structures, that is h1 of z, h2 of z, and hm of z. So like that, it can be moved up to the different stages, and each and everything will be realized separately. So h1 of z is realized and h2 of z separately, and till that hm of z, and then it will be added together. It is called as cascaded form. The next is going to be the linear phase realization. In that linear phase realization, it will be in the order of two structures. One is even, another one is going to be an odd structure. If the n value is going to be in even, you will be having this kind of a structure that is uh, up to this, that is x of z and y of z can be realized like this. And similarly, in the case of an odd, so the realization will be different. Okay, the same thing only, but the structure will be showing the difference in even and the odd. So we will move to an example one. So the draw the direct form structure for FIR system where h of z is 1 plus 1 by 2 z inverse plus 3 by 8 z to the power of minus 2 plus 5 by 4 z power minus 3 plus 1 by 4 z power minus 4 plus 7 by 8 z power minus 5. And here they have already given in the terms of z transform itself. Suppose if the values are given in the x of n or y of n, we have to take the z transform on both sides. And from this, we are getting h of z. H of z is nothing but output by input, y of z by x of z, and this is now final answer. And from this, what is y of z is x of z. In terms of input, we will be getting that equation. Always, whenever we are drawing the diagram, we have to start from the input and it has to end at the output. The first is going to be the x of z, and then it is having the delay unit of z to the power of minus 1, and it has to be multiplied with the corresponding multiplier 1 by 2. So 1 by 2 z to the power of minus 1, and it will be come to the adder. And again in this adder, I will be having this x of z also. So x of z will be joining here, and 1 by 2 z inverse will be joining here. So both are added together. So this plus sign is indicating this adder. And again the next term is z power minus 2. So one more delay unit will be added. Again the multiplier 3 by 8. So it will be added. So like this, it will move up to 7 by 8 z to the power of minus 5. So here, from starting from the input and to the output, all the structures will be added together and we are getting the final answer. Second is the example 2. Realize the following system with a minimum number of multiplications. Okay, that is linear phase structure. So h of z is equal to 1 by 4 plus 1 by 2 z inverse plus 3 by 4 z power minus 2 plus 1 by 2 z power minus 3 plus 1 by 4 z power minus 2. So we can able to write the solution as summation n tends to 0 to infinity h of n z to the power of minus n. H of 0 plus h of 1 z to the power of minus 1 plus h of 2 z to the power of minus 2. Up to this, it can keep on moving. And according to this, the given can be written as h of z 1 by 4 plus 1 by 2 z inverse plus 3 by 4 z to the power of minus 2 plus 1 by 2 z to the power of minus 3 plus 1 by 4 z to the power of minus 4. And if comparing the equations, I will be getting the terms. So H of n has to satisfy the condition H of n minus 1 minus m. So the impulse response is symmetrical. So it can be realized with a minimum number of multipliers. So here the equation after getting that h of z is equal to y of z, and this is our equation. So how to realize the structure? So here 1 by 4 x of z plus 3 by 4 z to the power of minus 2, and similarly minus 3 and minus 4. So how they are taking the terms to be, they are taking this 1 by 4 as a common, and these two terms will be getting inside, and 1 by 2 as a common, and 3 by 4 is getting separated. So by that they are drawing the diagram, that is 1 by 4 is a multiplier, right? So these two terms will be taken to the picture in the common adder, and then it will be multiplied with 1 by 4. And similarly 1 by 2 is common to z inverse as well as z power minus 3. So both will be taken together, and in the common multiplier they will be added. So like this they are reducing within minimum number of multipliers. The next example is find the cascaded form. So they are given a question. For this question, we have to draw the cascaded form realization of the FAR filter. So h of z is h1 of z into h2 of z. So h1 of z by y1 of z by x1 of z, and h2 of z by y2 of z by x2 of z. So like this, if I am separating, and similarly the multipliers are getting separated. So for this, they are drawing the diagram for h1 of z, that is x1 of z and y1 of z. And what is the multiplier we are having is 1 by 5. And 1 by 2 is getting separated. So if I am taking 1 by 5 as a common, x of z plus z inverse will be z to the power of minus 2 will be going taken in the common multiplier section. And similarly 1 by 2 is in the separate structure. So similarly I can do it for h2 of z also. Then they are added both together to have a cascaded form structure. And the next important point of this FIR filter design is windowing techniques. So windows, what are the windowing techniques? Windows are sometimes used in the design of the digital filters in a particular to convert an ideal impulse response of an infinite duration, such as sine function, to a finite impulse response filter design, that is called window method. So we are having different windows. So first is of a rectangular window. The rectangular window is represented with WR power n. So its function is 1. It is moving from minus 0 to n minus 1 and 0 hills. So it will be moving. So this is our structure of or representation of a rectangular window. The next window is going to be of a triangular window. The values are moving from 1 minus 2 power n modulus by n minus 1. So here the values are moving from n minus 1 by 2 minus n minus 1 by 2 to plus n minus 1 by 2 or 0 otherwise. So this is our rectangular window and triangular window representation. The next is going to be the Hanning window, and the next is going to be the Hamming window. Hamming window will be represented by WH of n, and here it's going to be the WC of n. And all these functions has to be well known to us. That is 0.5 minus 0.5 cos 2 pi n by n minus 1. It's moving from 0 to n minus 1, and similarly for Hamming window. Blackman window and Kaiser window. So these are also the different types of windows. So here. So totally rectangular window, triangular window, Hanning window, and Blackman window, and Kaiser window. So here what they are saying about the Gibbs phenomena. So this is an important phenomena of the windowing structure. So whatever may be the number of elements, the HD of n included in H of n, the magnitude of the overshoot and the leakage will not change significantly. When the rectangular window is used, the result is known as a Gibbs phenomena. The abrupt function of the impulse response results in oscillation in the passband as well as in the stop band. This effect is called as what? Gibbs phenomenon structure. So the frequency response of various filters we will be seeing. So low pass filter. So low pass filter will be that is only the allowable low pass is represented. So minus omega c to plus 3. And this is often high pass filter. Only the higher values will be passed. So from minus pi to omega c, and band pass filter. And this is for the band stop filter. So design of the FIR filters using window method. So how to design, what are the steps to be followed? We have to select a desired frequency and inverse Fourier transform for that. And the formula is HD of n is equal to 1 by 2 pi minus pi to pi ht of omega e power j omega n, and finite impulse response. H of n is equal to ht of n into omega n, and ht of n is a finite duration impulse response, and omega n is the for window function of finite function. And then we have to realize it finally. Okay. So here's an example. Design a low pass filter using a rectangular window by the samples. So they have given with the cutoff frequency of 1 by 2, 1.2 radian seconds. So they have given the number of samples are 9 and cutoff frequency is 1.2 radian seconds. So we know the frequency response of this rectangular filter is e power minus j omega alpha minus omega c to omega c. By using rectangular window, they have said low pass filter. So its corresponding frequency response we have taken. Step 1, we have to find out the hd of n. So what is the formula of hd of n? Already we saw from the steps. 1 by 2 pi minus pi to pi ht of omega e power j omega n, and we have to substitute all the values, and the final answer is sine omega c n minus alpha by pi sine n minus alpha. And if I am substituting that 0 and 0, it follows the L'Hospital's rule. And then we have to find out h of n. H of n is nothing but hd of n into that filter. Okay. So what windowing technique we are using is rectangular windows. So rectangular windows values also we know. So we have to substitute there, and we have to find out all the answers from n tends to 0 to n tends to 6 and up to 8. Okay, from the above, it is clear that h of 0, h of 1, h of 2, h of 3, and similarly this side h of 7, 6, and 5 both are equal. The values are minus 0.0792, minus 0.0467, 0.1075, and 0.2966. The last is in the transfer function, we have to substitute n tends to 0 to 8, h of n set to the power of minus. And if I'm substituting all the values by using the minimum multiplier method, and we can able to realize, and the final realization for that low pass filter by using the rectangular window is this. So at last we have designed a digital filter with the corresponding specifications. Thank you.